Welcome back to another session of Cloud Native series. And today we're going to be talking about how to run stateful workload on Kubernetes cluster. So what does that mean? So we'll try to understand today how to provide data storage or file system to the containers and hence pods running in a Kubernetes cluster on AWS, because that's where our cluster is installed. So the question is, okay, why it is important to understand this piece as well as a normal developer working in a Kubernetes environment. Why you want to understand how to provide data storage to your containers? Well, because not everything in your workload, the applications that you have been working and deploying, not everything can be stateless like your RESTful APIs, right? Which are just providing you the RESTful interface and then saving the state of your objects into an external database, maybe managed by a cloud provider like AWS RDS in that case, right? So not everything will be as simple as RESTful APIs. You will run into different scenarios. For example, Jenkins. When you deploy a Jenkins cluster, everything that Jenkins stores is actually on the file system, right? So it needs a directory to save the configuration, even to run all the jobs and all those pieces. Maybe you want to have a private Docker registry or NPM registry or maybe Maven repository for your infrastructure. And then maybe you want to deploy it on your Kubernetes cluster. So that's another important case. Maybe you need a cluster database, which is not available from the cloud providers. For example, Cassandra, not available on AWS, or maybe HDFS or Hadoop or Spark cluster or Kafka cluster or Zookeeper cluster. All of these applications require you to provide some sort of state or storage or persistent storage. So that's the target for today. That's what we will learn today to figure out how to provide data storage to the containers and to the pods into a Kubernetes cluster. So I'm Praveen Salitra, engineering lead here at Innate. We have been using StatefulSets and persistent volumes for a lot of stuff, including our Kafka clusters, Zookeeper clusters, our WordPress sites, our client's WordPress site, some other applications as well, including Jenkins and Nexus. So it's all coming from our experience of running and having everything containerized. So as I said today, after talking about how to install Kubernetes cluster, how to secure it using RBAC and AWS IAM, and then the last session when we talked about how to run pods and deployments and, in short, stateless workload. So the questions that we will be having today are, what is a volume? Because if you talk about container, and if you go into any other kind of scenario to Google about, okay, how can I provide storage to the container, the first thing comes into picture is a volume, or Docker volume to be precise. So then the question is, okay, understood how Docker volumes work. What about Kubernetes? What kind of support is there in Kubernetes for volumes? And then we'll understand what are different types of persistent volumes in Kubernetes. What if you want to involve AWS there? Because ultimately, you may be asking to create these EBS volumes, which are available from AWS, and same thing is available from almost all of the other cloud providers like Azure and Google. So you want to understand, what if a volume can be scheduled or can we provision a volume like this EBS volumes, elastic block storage, right? And if that is the case, who will provision it, how we can define size and all those kind of pieces, who can handle the life cycle of this volume available from the cloud providers, and then understand, fine, these are all simple use cases, but what if we want to run a replicated, distributed, stateful application or a service like Kafka or Cassandra, or maybe clustered MySQL Postgre version? Maybe you do not want to use the one available from your cloud providers. So those kind of situations. So that's another object that we'll talk about today called StatefulSets. And as usual, what are a few important things that we have learned working with StatefulSets and persistent volumes here at Innate? So we'll talk about some of those things. So let's start. So if we go back to this particular architecture diagram, the thing that we are talking about today is this piece where you see the volume, and the other important piece is this, the red one, which is running multiple containers maybe, but then you want to have each pod want to have its own dedicated volume, and that's the replicated stateful application like Cassandra or HDFS or a lot of these other applications are all about. So this is the configuration, how you deploy this kind of configuration. So we'll see by deploying a Cassandra ring today. So let's go back to where it all started. We know the container, which requires CPU and memory from the host machine to execute its task, both in terms of CPU intensive or memory intensive. Today we are going to be focusing only on storage. So in a container storage, of course, you have access to the container file system. The problem is whatever you write there in that file system of the container get lost as soon as the container is removed or destroyed or deleted. That means you should not write anything in the container file system if your objective is to persist it. If your objective is to keep it there and make it persistent even after the container is gone, yeah, you should not store it into the container file system. That's why if you go to any image of your MySQL or Postgre on hub.docker.com, the first thing that they mention is do not run without volumes. So volumes is actually a solution from the Docker where you can maybe map path inside the container to the host system or maybe somewhere else, right? And that's how it provides two different ways in which you can expose a file or a directory inside the container. So maybe let's say you have a MySQL container and you can provide CPU and memory from the container, but MySQL needs to store some data. It will store your database in the file system somewhere. By default, it will store it in the container. You may want to put it out of the container so that even if the container is going down and you are bringing it up, the data is still safe on your host machine, maybe on a block storage, maybe on a network file storage, and those kind of pieces. So from Docker, not talking about Kubernetes, but from Docker, you have two different ways of handling volumes or storages. One is via the volumes, which actually Docker creates every time you create a volume into this particular location, varlib docker volumes. This is on Linux or Unix machines. And ideally, non-Docker processes should not touch this location. This is supposed to be handled by Docker itself, because if you try to play with this location, you may corrupt the data. And of course, it is created and managed by Docker. So you can actually create a volume easily by saying docker volume create and name of the volume. What Docker will do, it will create a unique identifier for a directory within this location, and then it will try to store. If you mount this particular volume that you just created on a running container for a particular path inside the container, it will store all those files in that directory in that volume. So that's one way to handle volumes in a Docker container. Easy, you create the volume and then you use it using the mount point or the mount option. You say what is the source, in this case the name of the volume, and what is the path inside the container you want to map to this particular volume. So think of like when you plug your USB, your system detects that a USB hard drive has been added and it mounts it on a specific drive location, right? On your devices, maybe it's Mac or maybe on your Windows. Something similar we are trying to do here as well. Think of it as an external storage to the container, external to the container, okay? And then you are mounting it within a specific path within the container, because remember, container is also a Linux system. Other way, where if you don't like to create volumes here in this particular directory and you don't want it to be managed by Docker, other way to do it is using bind mounts. And in that case, a file or directory which can exist anywhere in your host machine can be mounted into the container. Now it's all up to you about how you want to handle it. Maybe you have non-Docker processes, you can go and modify and all those pieces. Here you don't create a volume explicitly, you just run the container by providing this option of the type bind, and you say, okay, this is my relative directory in the host wherever I'm running the Docker, and then this is the target inside the container. Simple, easy stuff, but then this is one way which is more popular than creating volumes if you are directly dealing with containers. Volumes is mostly used when Docker is handling its own, maybe using Docker Compose, and then of course we'll talk about Kubernetes, how it handles that. So if that is clear about how we can mount certain storages, maybe those are on the host machine, maybe those are on the network drives, maybe those are any kind of external drives, including your elastic block storage, if you can think about it. So two different ways to mount those things inside the specific path inside the container. Okay, so we understood that. Now the question is, all good, how Kubernetes handles volumes, because we don't run these commands to run Kubernetes pods. So in Kubernetes, if you remember the first architecture diagram that I have been showing you, we had one pod which is running one container and has some volume. The other one had two containers which are, of course, will be sharing volumes within that pod. So you have seen this in various fashion that we have shown so far. So let's understand that. One of the difference with Docker volume versus a Kubernetes persistence volume is, in case of Kubernetes, the lifetime of this volume is actually dependent on the lifetime of the pod. So what does that mean? Well, even if this container goes down while the pod is still alive, if the container goes down or it's getting restarted, the volume will still be preserved. So you don't have to worry about it. Unlike the other case where if you are using the Docker volumes, not the bind mounts, in that case, if the container goes down, the volume will be removed or will be unusable next time the container comes up. In this case, until the pod is alive, the volume is alive. The volume is not tied with the lifetime of the containers inside it. So that's one benefit you get, because maybe your container can get destroyed or maybe restarting it, but the pod is still alive, right? So your volume can be kept there as it is. Data is preserved across the container restart, as I explained. Each container in the pod must independently specify where this volume should be mounted within a specific path. Same story as the previous Docker container example. So if you have the volume, but just attaching this volume to the pod definition or the pod spec doesn't mean it will be available to the containers. Containers have to mount it similar fashion like this inside a path inside the container. So this is a pod spec, and the bold items here is what I have added new. So think about it, what we have here. So this was all same, but here, apart from containers, you have an entry for volumes, and you can have a bunch of volumes, a list of volumes. You can name it, and in this case, let's say I'm deploying this pod on AWS. So someone, maybe the admin of your AWS cluster, has to go and create a volume of the type AWS EBS, Elastic Block Storage. It will have an ID, it will have a file system, and you attach it. Let's see one example here. I'm not going to create a volume. So for example, these are all the volumes, EBS volumes created by KOps for your cluster. These are not to be used by your applications. In this case, I'm trying to create a new volume for my application called Whale app, which we have seen running before. So if that's the case, what an admin would have to do now is to go here, create a volume, use the GP2, which is the general purpose SSD volume type from EBS, from AWS. You say how many GBs you need and then where it should be deployed. And ultimately, if you create it, you will actually, I did not create it, but if you create it, you will get an ID, volume ID, which is unique. So if that's the case, you get that volume ID and put it here. So that's one part. You actually are binding that volume definition with the pod. The next thing is you have to use this volume that you have, whatever the name it is, and you have to mount it in a specific path within the container. So each container that you have will have an entry for volume mounts, which can be a list of mount paths. And here you are saying, okay, that volume, which is this friendly name, use it and mount it or make it available as a directory inside some path, whatever you specify here in the mount path. So this is an example of how you can have volumes mounted or into the container, but first you have to attach it to the pod definition as well. And you can clearly see issue here that as a developer working in the Kubernetes environment, and let's say you are not the admin, you do not want to hand off this sort of capability to your developers. They will not have access to creating volumes if they don't have access to your AWS EC2 console, or if they don't have proper IAM authorization to do that. And that's going to be very much problematic and non-scalable scenario, because you may have hundreds of applications. Your developers may be trying out hundreds of different things with volumes. They are not going to be sitting there for your DevOps to create this volumes on every Jira ticket that they open. So it's not a good developer experience, to be precise. Before solving this problem, let's understand what type of volumes are available that Kubernetes supports. So we already saw EBS. On Azure, you have disk and file. Config map, think of it like a hash map or just a property value map that you can provide to Kubernetes. It's a type of Kubernetes object. Empty directory, if you want to just use something like temp location, right? In a Unix system, you usually use temp directory for something, so you can have an empty directory kind of volume attached to your pod, and you can write it, and it's useless, to be precise. On Google Cloud, you have GCE, persistent disk. Then there are some other volume providers as well. GlusterFS is one of them. A lot of other stuff coming out here as well. Portworx is a very famous volume provider or a storage provider for Kubernetes. So, and these are all mostly based on NFS concept, network file storage. Today, we are going to be focusing on EBS. We understood the concept a little bit, but we don't want to do this thing manually. We want to somehow tell Kubernetes, you know what? I will just tell you I need 5 GB, 10 GB, X amount of storage. You find it out. You already have CCM, remember? Cloud Controller Manager. So why don't you work directly with EC2 and create and manage a life cycle for the volume that I'm asking for? And that's exactly Kubernetes has done. So the way a normal developer, not an admin, a normal developer can ask Kubernetes cluster via this particular object called PVC, which is persistence volume claim. And easily, as the name suggests, it's a request for claiming a specific size of volume, right? So it's a very easy abstracted way to claim a storage, and you don't have to be admin to claim this. But admin initially, while setting up the cluster, has to specify a few default storage classes, because for example on EBS, if you remember, there was some option, right? You can choose one of this for your volume. So your volume or your admin provider or your admin has to specify a few default choices there. And of course, a normal developer who has access to Kubernetes, any namespace, can create a PVC, a persistence volume claim. You don't have to be admin, because for the persistence volumes, you have to be an admin. But for persistence volume claims, you don't have to be admin. And that's what most of the applications that we use today will be using. They will be asking, or they will be claiming for a persistence volume. It's like requesting or creating a request, oh, give me 10 GB of storage via EBS. And then of course you can ask whether you only want that block of storage for read only, or maybe read and write both. Usually you want to read and write both if you are putting a stateful application. Then of course, as I said before, admins can go and create a storage class, which can be default one with default values. Maybe you want to say, you know what, any claim that comes in this AWS cluster for Kubernetes, I want it to be using GP2 type, which is the first type, the SSD type of it, right? Maybe the default size of all of this, and you can set up those things. The good thing is, when you install Kubernetes today, you actually already have a storage class defined and defaulting it to GP2 here, which is why, because KOps installed it for you on AWS. So if I just go and just see what's there in this particular GP2 storage class, everything is simple. It is an object of the type storage class. It is of GP2, right? There are some add-ons that has been added to it. Important thing is it's available as the type GP2, and that's it. And of course, who is provisioning it? AWS EBS. So CCM is getting utilized here to handle this sort of storage classes. So once that is already defined, you don't even have to create that storage class. It's available to you by default if you install Kubernetes on AWS using KOps. Another important thing, which we will see a little later down the line, is let's say today I'm asking for 10 GB of storage. Maybe I am not sure, but maybe let's say we are using it for Cassandra ring, right? And then maybe tomorrow we want to expand that persistent volumes, right? More than 10 GB, maybe we want to make it 100 GB. Now, depending on the cloud provider, for example, on AWS, your EBS volumes can be expanded. So that feature was also added to your persistence volume claims as well, starting 1.11 beta. You have to make sure that you enable a certain flag. The chance comes or requirement comes to increase the volume of an already claimed storage. You should be able to do it. Another important thing is your persistent volume claims are tied to the namespace. So wherever you create a PVC, it is tied to a namespace. But on the other hand, persistent volumes, these things are actually tied to the cluster scope, and that's why you need an admin to create a persistence volume. So there is a difference. You can create a request for a volume that is tied to your namespace. So maybe your dev environment can create or ask or claim for a PV, which can be separate for the same name PV in staging environment or a prod environment if you are using namespaces for environments. And they will all have unique identifiers. So simple commands to get claims or the listing of PVs. And since I'm admin, I can access PV as well. If I was just a developer, PV will not be allowed. So if I try to see dev and do PV, I can't because it's a cluster scope. But if I do get PVC, it is available because PVC is a namespace scoped. Let me become admin again. Okay, so we understood persistence volume. We saw the definition a little bit, but then if you remember, we don't want to use pods. We want to use deployments, right? We answered this question last time in the last session. Here it was a pod definition. Pretty simple with the deployments as well if you want to use it there. So what do? You create a claim using this template. And what are we asking here? Okay, it is an object of the type PVC. You name it. You say what mode you want, whether you want read, write once, whether you want read only, and there are a few more options available depending on the cloud provider, and then you say how much storage do you want. And I'm asking 2 GB. On AWS, You cannot have less than 1 GB of EBS volume. So I tried many times asking for 500 MB or 100 MB. It's not allowed. Minimum is 1 GB there. So anything more than that is fine in PVC on AWS EBS. The next thing is, okay, this is just claiming that volume. What if we want to attach it just like we attached and mounted on a container in a pod? So how do we do it with the deployments? Pretty simple. Rest of the stuff is pretty standard. Name of the deployment, name of the app, the labels to match it, name of the container, image, ports, everything. Yeah, this is the important thing here. So instead of giving the volume ID from your AWS EBS, you just refer to the name of the PVC here. So there is a property called persistence volume claim in the volumes list. You just refer to the PVC, and that's it. Nowhere you have to have understanding of whether it's in EBS, whether you are on AWS, or whether you are on Azure, or whether you are on GCP, right? Because nowhere here it talks about what cloud provider you are talking about, right? So in this case, since I have not used any storage class, it's going to use the default one available. And in our case, the default one is GP2, which has been set by the admin, in this case, KOps, when we install the cluster. So let's try to deploy a MySQL database with a persistence volume. So let's see what do we have here in this particular YAML file. As a Kubernetes user, I'm asking or claiming or raising a request for 2 GB of storage. And nothing I know anything more than this. How it is going to be talking to the AWS EC2 to create that volume, I have no idea, right? It's all Kubernetes job, not mine. I'm asking for a specific name, give it a specific name, and make it available in the dev namespace. Fine. This is new thing which we have not talked about it before, but it's very important to understand as well. In Kubernetes, you can actually create secrets as well. Think of any scenario where you had to pass database username, passwords, or any other confidential information to your applications, right? You usually pass it using environment variables, and you think, well, my cluster is anyways private, no one would know it, but your developers know your credentials for your production servers, databases, everything, right? It may not be accessible because you may have some certain restrictions on who can access the databases in production and all that, but still, if you do not use proper concept of secrets, both in Docker secrets or Kubernetes secrets, you are exposing those values, those credentials to your developers or to your DevOps team, and not to any specific set of InfoSec team. So secrets is one way to do it. Ideally, you do not want this to be handed off to the developers. Maybe your InfoSec team manages secrets into a private Git repository, which is not accessible to anyone in your team except the InfoSec team, right? And they can maybe manage this, committed this particular object. In this case, as a developer, I have access to it. I'm creating a secret. So the name of the secret is MySQL secrets. I have a property or a key there, and this is the value. This is just base 64 encoded value. So if I just go and see, very awesome password root. So that's one piece of new thing that we have not discussed before. But then let's go back to PVC. We have asked for 2 GB of storage, and then here I'm asking, okay, I'm deploying a MySQL app, only one replica. Remember, if you are using deployment with persistence volume, make sure your deployment is only having one replica. Otherwise, there is no guarantee which container is which part is gonna be talking to what volume, and it's all gonna be mess. This is not the place if you want more replicas with persistence volume. StatefulSet is the object for that, not deployments. But in this case, let's say we have figured out and we have set the limit that, you know what, for this particular MySQL, it will be single instance of this part. That's why it's fine to use persistence volume with deployments. In any other scenario, that's not good. We'll talk about this. But anyways, so make sure you have number of replicas as one, standard stuff about the template metadata and everything else. I have just one container here. You can have multiple containers, fine. It's gonna use MySQL 5.7. I'm opening a port 3306. I'm naming the port. Again, we understood this. Since we were using secret, so instead of passing the value like this and saying my password is root, you can actually ask it to get it from a secret reference, right? The name of the secret is MySQL secrets, and what property are we supposed to use? This property. So this is one way in which you can still pass secrets to your containers via environment variables. But then still, if no one has access to this secret, maybe your only InfoSec team is managing this in a private Git repositories and refreshing them directly to the production clusters, fine, this can be completely out into a different deployment process. But here we are saying, find out if there exists a secret with the name this, and find out the key, and whatever the value it is, yeah, that's the value of the root password. This is one of the environment variable that the MySQL image needs. And then here, same thing. We want to make a volume available to this pod of this deployment, and the PVC is named like this. So it will try to find PVC in the same namespace. It will find, because it's the same name here, MySQL PVC. And then once I have it, I'm attaching or mounting it to the container. So this definition is actually for the container, not for the pod here. And I'm saying, you know what, MySQL data, yep, the volume that I named it like this. So this is the path inside the container, and this is the path inside the volume. Think of volume as a hard drive that you are plugging it. So you are telling container that, okay, whatever you are storing on this location, don't store it on the container file system, store it onto this folder inside this directory or this drive. And then just for this example, I have done few more things. I have created a service as well so that I can access MySQL from, at least in the cluster, right? From there, maybe I want to reach out to it using MySQL colon 3306. So I have this service. We have understood all these concepts in the last session. One interesting thing I'm doing here is I don't want to do command line, so I'm going to launch a PHP MyAdmin, which is a web user interface for accessing your MySQL databases. Again, pretty standard deployment for PHP MyAdmin, one replica. The image is coming from here. It runs on port 80, fine. It needs where is your MySQL server or how it can be reached. So since it's a service, right, which is cluster IP by default. Remember the last session, cluster IP services. So it will be available as name of the service dot namespace of the service dot svc dot cluster local. So I'm passing that information to PHP MyAdmin. Think of it as a front-end application for your MySQL database. And then I'm saying, okay, it's available on port 3306. Ultimately, I want this to access from the UI, right, from my browser. So I'm saying, okay, this PHP MyAdmin service deployed as with the type load balancer. Behind the scene, it will create a AWS ELB for you so that you can access PHP MyAdmin, and from there, within it, it will internally, within the cluster access only, it will talk to MySQL on this port via this service. So we have created a lot of objects in the same file. So let's just go and apply this configuration and see what happens. Yeah, so this many objects have been created, a persistence volume claim. Let's just go and quickly see what's the status of it. So it is being asked right now. So think of a request is getting raised from this PVC, and within few seconds, Kubernetes will actually provision a 2 GB with this unique volume, and it is of the type EBS. So if you go and refresh it here, you will see that guy coming up with 2 GB somewhere. Yep, this is the guy. It has a name as well. It has the unique identifier as well, which is exact same stuff as here. So get PV is actually cluster scope. PVC is in the namespace. So I have this. Then let's see the status of what else was created. A secret deployment for the MySQL single instance database, a service to reach out to MySQL database. Then we just wanted to access it from the web browser, not from command line. So I have installed PHP MyAdmin and a service, a load balancer service for that. So let's see. Of course, I have two pods running now. One for the MySQL, one for the PHP MyAdmin. And since PHP MyAdmin is a load balancer type service, as we understood last time, we should be able to get an ELB name like this. And you can also see it will be coming up slowly. It's an asynchronous request. Yep, this is the one. Dev namespace PHP MyAdmin service. So if I just hit it, since it's running on port 80, I don't have to specify any port. Within few seconds, it will come up. So that's pretty simple and easy way to deploy and work with persistence volumes, and more easy or very easily with PVCs, right? You just have to specify how much size you need. That's it. Just checking if it's available. And yep, PHP MyAdmin came up. The admin username of a MySQL is always root, and my stupid password is also root. Remember that awesome secret? This guy? Yeah, that value is base64 encoded root. So if I go there, yep, I have the default schemas available. I'm just gonna create a new one. Let's say this is UserDB. I'm just gonna create just standard MySQL database. I'm just gonna create a new table. Let's call it users. Just 2 columns. Go for it. What is it? First name and last name. Definitely not integer. 256. 256. Save it. So ultimately you have a user table with nothing in it. Let's insert few things. So let's say Praveen Solitra. I'm just gonna insert one row. And you see one row is already inserted, right? So this is how usually, not in this fashion, but that's how your database will be used going forward. Maybe there are services or APIs hitting your database running here. And then maybe one day your database will go down. So I'm just gonna delete the deployment. And let's see if the persistence that we have here, we should be able to save this user DB database with the user table with this particular row already inserted, right? So let's destroy the deployment. So pod we have deleted now. So if you go there and check, there is no pod. There is only phpMyAdmin running, which is gonna start complaining now because it will not be able to find a running MySQL container. The good thing is when the deployment is destroyed, your PVC is not. So your PVC is still alive. That means your volume is also alive. So you're not losing anything if your deployment, your pods are going down. That's one good feature. So the storage block will still be saved and available to you. Let's bring the deployment back. I'm just gonna apply entire PVC back. Rest of the stuff is unchanged except this deployment has been created again. And again, remember, PVC was alive. Now the container is getting created. The same data that was there before in the PVC in this location will be mounted on this location. MySQL is smart enough. It will go and understand, oh, okay, I already have the database running there. So this is running. If I hit phpMyAdmin again, this time it did not complain because it found a listener on MySQL 2306. And if you go again, your database is intact, your table is intact, your data is intact. Cool. Pretty simple example of how Kubernetes volumes can be used, which will persist your data if you want that way. Cool. Okay, so I'm just gonna get rid of all of this, all the objects that I had in that block, including the PVC. As soon as you remove PVC, that's gone. And even the tied PV is actually getting out now. It will be going out in a few seconds. You see, this is getting removed now. It's getting detached, then it will be removed. That was all about persistence volume and deployment, right? How do you claim it? You just use a PVC object. You don't have to know anything more than just how much storage do you need in terms of GB. And then you try to attach first to the pod, and then you mount that particular volume to a specific path inside the container. That's the only thing you have to learn. And that's how you can do a lot of good stuff. Wherever your intention is to have stateless applications, of course, you will be using deployments. And if you want to use a stateful application, but with only one replica, I would suggest going with the example that we did, deployments with PVC or PV. Condition is one replica. Because if you increase number of pods to more than one, and if you are using persistence volume, it's like two containers trying to hit the same directory, and of course they will mess up the consistency of the data in that directory in this fashion, because there is no sync between containers running in a deployment. It can start at the same time. There is no ordered fashion. Nothing is consistent if you are using multiple pods with the same PV. Don't do that unless your intention is to only do read only from the pod, not the write, because issues will only be in the write. Right? If it's read, you're fine. Go and deploy 10 replicas of the pods and use only one PVC, fine. But if it's read and write, yeah, good luck. Don't do that. The question is, okay, at the start of this session, we talked about replicated, distributed, stateful applications, which needs persistent storage. For example, you may have data nodes in your Hadoop cluster. Maybe you have data nodes in your Cassandra cluster. Maybe you want Kafka Zookeeper cluster with more than one brokers, right? Now, in all this scenario, including, of course, if you want multi-node, multi-cluster, or a clustered Postgre or MySQL database, in all of this scenario, you have data nodes with a dedicated persistence volume, which is not shared with other instance or other slave in a master-slave configuration or other masters in a master-master configuration like Cassandra. So if that is the case, what's the answer? Well, before going into the answer, what do we need for all of these pieces in this fashion to run, right? In this replicated persistent applications. So we need an ability to not just do read only from multiple replicas. We actually want read and write access to the volumes by each replica, each pod independently. Each data node wants to have its own dedicated volume, which no one else is touching. But then you want to have multiple replicas of this kind of nodes, right? That's what all these clusters are all about. When you deploy, you want all these pods to come back one after another. So you want an ordered, graceful deployment. And if you scale, let's say today you say, oh, I'm going to be using 3 pods or 3 replicas of the Cassandra ring. Tomorrow I'm going to increase it to 12. You want to make sure the scaling is also graceful, meaning it's not like just creating pods here and there without thinking about volumes and all that. And another thing with all these clustered applications is they have their own load balancing, or they have their own way of reaching out to the slaves and other data nodes. For example, in case of Kafka, you need to have individual identification or individual service or DNS for all the pods, right? Called brokers there. Same thing goes for the Cassandra ring as well. Same thing goes for the Hadoop and all these pieces. They have their own mechanism. All these clustered applications, they have their own mechanism of doing service discovery and then also reaching out to individual replicas. So that means you don't want to use the Kubernetes service for that, the traditional way that we know of the service in Kubernetes, which does load balancing across multiple replicas and all that. So how do we come up with a solution which can do all 3 of this? And that's where StatefulSet comes into picture. It was kind of a delayed entry into Kubernetes ecosystem, but it came and kind of helped revolutionize about how you can manage and deploy all these clustered, replicated, stateful applications. That's why the name StatefulSets, sets of stateful applications. So in this case, think about it. You want to have proper naming, not like this random pod name, if it's still there. I removed. Yeah, you don't want to have it because ultimately your masters of these clustered applications want to reach out to these pods via well-defined name and all those kind of pieces. So it is definitely used to manage distributed, replicated, stateful applications. It maintains a sticky identity instead of giving a random ID to each pod, which will make it very hard for services to figure out as well. It actually just uses ordinal index, so something like 0 and 1 and 2 after the name of the stateful set itself. Pretty easy, we'll see. And then it provides stable and unique network identifiers so that maybe the master wants to reach out to all the nodes, all the pods in a Cassandra ring in a sequential fashion or whatever it wants to do. Master would want to talk to them individually, maybe for replication of the data, right? So you want all the pods to be identified uniquely on the network, which is not what happens when you use a Kubernetes service. What happens in that case, you just use one DNS, and internally Kubernetes service will be doing load balancing across pods. So far this thing never required, right? But now it is required because all these clustered applications have their own way of talking to these individual nodes. They don't want to use your awesome load balancing from Kubernetes service. Ultimately, of course, you want stable and persistent storage. You want to have stored, ordered and graceful deployment, scaling, automated rolling updates if you are updating an image or a new version of this app. So these are some of the things that are provided by StatefulSet. One thing that it does same as deployment is when you delete the StatefulSet, it does not delete the volumes associated with it just to preserve your data. Maybe you want to delete StatefulSet and replace with something else using the same volumes. You can pretty much do here as well. And then for this particular piece of unique network identifier, Kubernetes only has services, right? But the problem with the normal Kubernetes cluster IP services or anything else is they will do load balancing. So how do you avoid doing load balancing? Well, you just say cluster IP equals to none. That's it. We'll create a headless service for that. So that's how you do. And then there is a pretty simple naming convention where master can reach out to individual nodes in this clustered application, and they can do all their load distribution themselves. So what do we need? We need a headless service for the identification on the network side for each individual pod. We need how to define the stateful template, just like a deployment spec. And then we need how to claim volume, right? We have already seen this piece, which is PVC. There's a different syntax here as well, which you can dump into StatefulSet as well. We'll see. So you need a service, a headless service, which will allow you to not do load balancing, but individually reach out to different pods, different replicas in this StatefulSet. The only difference with a normal service is here explicitly we are saying cluster IP is none. By default, it's cluster IP. Pods will be given IPs and all that. In this case, no such IP is given. Kubeproxy is not even gonna coming into picture to do any load balancing or anything with the routing table. It's gonna directly managed by the masters of these clustered applications. Clustered applications like Cassandra, Kafka, Zookeeper, or maybe your Postgres, MySQLs in a cluster fashion, HDFS, whatever you have. And this is StatefulSet. Pretty much same. almost same as deployment except few individual properties. So here you say it's type StatefulSet, name of it, and this property you need now, which was never there in deployment. Here you have service name, so you have to tell what headless service you have created, so which is this part. And then, okay, I want 3 replicas, each having 1 container, exposing on a specific port and all this stuff. And then each container is asking for 20 GB of GP2 volume, which is mounted in a container on this path. Almost similar, except instead of calling for volumes via PVC, we are saying each replica will have its own claim. Instead of having a combined one claim for all the replicas, we are asking for each pod having its own claim of 20 GB. So this is similar to the PVC, but this time this is actually part of the pod itself. So if there are 3 pods, that means there will be 3 20 GB volumes created by Kubernetes for you. So I have an example of that as well. Let's deploy Cassandra in Kubernetes with 3 nodes. What do we have here? I have created a headless service, cluster IP none. That means it's headless. There will be no entry in kubeproxy for this. It will not be doing load balancing. Every pod will be reached out individually, and we'll figure out what's the naming convention there. I'm opening port 9042, which is CQL or CQL port. And then this is the stateful definition. Again, I'm not going into details about Cassandra. Focus is to understand StatefulSet. The service name is Cassandra, which is this name. I'm asking 3 replicas, standard stuff for your selectors and your pod selectors and your pod labels. Containers. So I'm asking, I need 1 container. I will name it Cassandra. This is the image from GCR. These are the ports that I'm opening, which are again required by Cassandra node. This is again resource limitation that we talked about last time. Limits and requests both in terms of CPU and memory for this node. Now, a specific thing that most of these clustered databases like your Elasticsearch, if you want to deploy in a clustered fashion, Cassandra, Postgres, MySQL, they want each process to log the memory. So a specific flag has to be passed like this. You can read more on kernel.org about IPC lock. If you ever want to execute something after the start of the container or before the stopping of the container, you can actually subscribe to this lifecycle hooks, and then you can execute, for example, here, just before stopping this container, there is a tool in Cassandra world called node tool. You are draining it, and then some environment variables. In this case, I'm providing the value of this environment variable from the same pod template. Here you have some max heap size, mean heap size, Cassandra clusters names, data center name, rack, all this kind of Cassandra specific variables. This one is the interesting one. You remember we said in case of most of these clustered applications, these masters and even these clients, for example, if you have a Kafka client, masters of these clustered applications or these clients, you just provide them all individual nodes DNS or a way to reach out to these individual brokers, individual masters, individual nodes, individual data nodes. You don't want to put any load balancer for that, right? They are all capable of. That's why they are clustered applications. They understand how to deal with talking to individual nodes if it's more than one instance of these clustered applications. So if that is the case, that's why, remember, we did not use the normal cluster IP service. We used a headless service. So that is the case. Then the way it works is this piece is known. Name of the service, dot, namespace name, dot svc cluster local for the internal cluster only available DNS. And then in front of it, it just puts the pod name of it. How can we have a pod name like Cassandra 0? Well, remember, in case of stateful apps, the IDs are actually using ordinal index. They are not some random IDs like this for the pods. So in this case, what's happening here? Masters, or the seed one, the first one, will be this particular pod. So it's a way directly to reach out to that individual pod. Remember how many pods we are asking? 3. So there will be 3 pods, Cassandra 0, Cassandra 1, and Cassandra 2, because you want a strict mapping between the pod and the volume and the network identifier. So that's how StatefulSet is trying to do that. So name of the service, headless service, namespace name, SVC cluster local, but in front of it now, you want to put specific pod IP or pod DNS as well. The rest of stuff is what? This is environment. Yeah, how to check whether this pod is available. Well, there is a readiness. Usually use HTTP, but in this case, in Cassandra's case, there is a shell script already available. So you just ask to execute after 15 seconds of initial delay, and if it does not respond in 5 seconds, call it dead. So that's a readiness probe. And then this is your stateful part or volume part. You're asking 1 GB of volume per pod, and there are 3 pods you're asking. and this is the claim template, and then you are mounting this pod within wherever the Cassandra is storing the data. It's called Cassandra data. So let's go and apply StatefulSet, right? We are deploying Cassandra with 3 nodes in this Cassandra ring using StatefulSet. Each node in this Cassandra ring will have its own dedicated 1 GB of storage. So it's created. Let's go and check the status of it. So you see we asked for 3. Currently 1 is there. And if you go and check the pods, you see we're just waiting for 1. Why? Unlike deployments, as soon as you say I need 3, it will just go and bombard and create all those 3 pods for you. In case of StatefulSet, you remember this? It's an ordered, graceful deployment and scaling. So it will start with 1. Behind the scene, it has asked for a PVC of 1 GB, right? Which will have a mapped PV, 1 GB, right? Which is tied to this PVC, and this particular PVC is actually getting tied to this Cassandra 0 pod. So if you describe the pod, so you see it has this PV attached. Name of the claim is 0. So everything is identifiable here using ordinal index. And the container is started. So let's go. So only after when the first one was successful, the second one is starting. The whole point of ordered, graceful deployment and scaling, right? ST is a small form for stateful sets. So I have asked for 3. 2 of them are getting deployed. So it's working out. Maybe let's check the logs. Cassandra uses JMX to talk to other nodes in the cluster. So all of these pods have their own IP, but the way they reach out to each other is using the headless service that we created, but putting pod name in front of it. Okay, both of them are running. Third one is getting created. Let's execute a command, if I remember it correctly, to check the internal status. What is it? Node tool status. It will tell us to the pod 0 what it looks like to itself, right? So of course it could find two nodes in this Cassandra ring. Both of them are up and normal because of course the third one is still getting created. Well, this is just coming online. At least the PV was applied to it. If I ask Cassandra 0 again, okay, how many nodes do you see in this ring? It will say, okay, I see 3 now. 2 of them are up and normal. 1 is up and joining. Okay, so it will come up and running, but at least you got the idea. This is a Cassandra ring deployed in a Kubernetes. You have 3 individual 1 GB volumes, each tied to one of the pod, right? So Cassandra 0, Cassandra 1, Cassandra 2, tied to all these individual pods. They have all dedicated volumes. So that's the whole point, how you can run replicated stateful applications in Kubernetes. Cool. What you have to understand, of course, there are a few internal details of that applications you always have to understand, right? The properties or environment variables you want to send and some other details. But you can go ahead and deploy any number of nodes now in your Cassandra, in your Elasticsearch, in your Postgre, in your MySQL, in your HDFS, in your Spark cluster. Okay, so all 3 are up and running. Yep, all of them are up. Okay, if you understand basic concepts of Kubernetes objects, everything else going forward is so easy. Everything is just YAML. So last slide, things to remember, and these are coming from our experience working with persistence volumes and stateful sets. There is a specific gocha with EBS volumes that you have to keep in mind. EBS volumes in AWS cannot be used across availability zone. So make sure you have more than 1 node in your Kubernetes cluster per AZ if you are using EBS volumes. So the nodes on which your pods are running must be, of course, AWS EC2 instance. What else you thought? Those instances need to be in the same region and availability zone as the EBS volumes. By default, Kubernetes will take care of it for the first time. So let's say if your pod is getting deployed on US East 1A, it will ask for persistence volume in the same availability zone. EBS volume only supports a single EC2 instance mounting volume, so you cannot think of I have 10 nodes in my EC2 cluster and I can use one volume and map it to 2 different nodes. Yeah, that's not going to happen. So that's one limitation of EBS volume. It's not a network file storage, right? It's just a block storage for that EC2 node. Yes, you can use EFS, Elastic File Storage, which is, think of it like NFS from AWS or network file storage from AWS. You can use it. You have to create your own storage class for that. So just like GP2, you can create your own, name it. It's just a YAML object anyways, right? So you can create it and then maybe you can ask, for example, here, when your StatefulSet is asking for the storage, you can, instead of naming GP2, whatever you have for EFS, yeah, use it. Or maybe any other file storage that you can think of. As I said before, deleting StatefulSet does not delete volumes associated with the StatefulSet, just to preserve your data, even if StatefulSet is going down. Another thing is, if you just terminate StatefulSet, that termination is not graceful. So the way when you started StatefulSet, it brought one pod after another. But if you delete the StatefulSet, yeah, all of them will be terminated together. If you don't want it, I would suggest scaling it down first. So right now, all 3 are running. So if you just go and say delete STS, whatever the name is, Cassandra, all of them will be gone at the same time, just like deployment. So there is no graceful termination. If you want to have graceful termination, I would suggest scale your STS. What is name? Cassandra. And say replicas. So scale it down to 0 first. And then you can go ahead. So you see, one is going down. Once it's done, then only the second one will go down and the third one will go down, something like this. So yeah, if that matters to you, make sure it is there. Another thing is, as I explained before, many times you may want to just put any size of the storage for the first time you create it, but later down the line you may be required to increase it. It's a feature available from AWS EBS, and here, in order to make it available, it's still in beta right now, but you can use a lot of things in Kubernetes even if they are in beta. Alpha are the problem ones. So it has been beta since 1.11, which was, I think, mid of this year. So you have to make sure you have this flag turned on your storage class. Right now, I don't think I have this turned on this storage class. Yeah, it's not there. So you may have to edit and then turn that flag on. So that's it for today. Next time will be interesting. So you remember last time when we talked about service of the type load balancer, there was a specific issue with the cost. Let's say you have 100 services and you want to expose them to the web, maybe even to your internal network, private network. But if you are using service of the type load balancer, it will be very costly because each load balancer costs you on all the cloud providers. So how do you manage that, but also give a nicer seamless flow of load balancing from outside world? So we will talk in the next session something called ingress controller, and then we'll also understand, you know what, I want to run all communication on HTTPS, even if it's for the dev servers or the staging or everything. The problem with SSL certificates or HTTPS, whatever you call it, they are expensive if you go and purchase it from AWS or GoDaddy, right? They are all costly. If you want to avoid that cost, we will also understand how we can configure automated Let's Encrypt certs, which is free. So in the next session, we will understand first how to use ingress controller so that we can have only one load balancer and then everyone is routing request for all the HTTP requests via it. And the other one is how to save money using Let's Encrypt. So it's going to be pretty interesting in the next one. And the one from then will be, we have all this stuff, critical stuff, mission critical stuff running on Kubernetes cluster, how we can do or manage disaster recovery and then also monitoring. So that's it for today.